Now, just to give you an idea how this stuff will help us in organic chemistry, let's combine it with something that we learned before. We can actually use these concepts to solve this problem. And this problem is asking you, what are the relative percentages of each chair conformer of methyl cyclohexane at room temperature? So let me walk you through how to solve this problem and notice the equations that I use. Now, let's take the time to understand this question first. What is methyl cyclohexane? Well, here's one version of it at least. And notice I have a chair structure and I got my methyl axial. We know that this structure can ring flip, and if it does, this is what it will look like. Now, not exactly. However, we know that the methyl will no longer be axial, it'll be equatorial. So this is good enough for right now. And let's even label this. Let's call this A, the amount of molecules that adopt this particular conformation, A for axial, and this, E, the amount of molecules that are adopting this particular conformation with the methyl group equatorial. Now, remember, we learned in a previous online lecture that axial substituents always have the 2,1,3 diaxial interactions. And notice it's our structure here on the left that has the axial, and the structure on the right that has the equatorial. Now, take my word for it, it just so happens that a 1,3 diaxial interaction, its energy amount happens to be 3.6 kilojoules per mole. Some textbooks have it at 3.8, but for this problem it's a trivial point. We're just going to go with the 3.6. So that means to calculate the total energy worth of the chair structure on the left, since remember every axial substituent has the 2 interactions, that would be 2 times 3.6, which is 7.2 kilojoules per mole. So let's note that the total energy of this molecule would be 7.2 kilojoules per mole. Now let's do the same analysis for the other chair structure. Remember, if a substituent is equatorial, then it has 0 1,3 diaxial interactions. Therefore, let's say that his energy level happens to be 0. Now, here's another thing I'd like you to do. Let's pretend that what we have in front of us is a reaction, as in this would be the product of the reaction, and this would be the reactant of the reaction. We'll see why we're doing this in a few minutes. And let's do this now. Let's do some math. Let's say we wanted to calculate the change in energy for this quote-unquote reaction or process. Well, remember, the change of anything is always final minus initial, or in this case, the energy of the product minus the energy level of the reactant. And we previously calculated that. We would say delta E then is 0, the energy of the product, minus 7.2, the energy level of the reactant, which means delta E is going to be negative 7.2. Now we're ready for the next mathematical step here. We're going to use this equation from thermodynamics. We know this equation as delta G equals negative RT natural log of KEQ. But for this particular problem, delta G and delta E are the same, so we're going to use them interchangeably here. But let's do some algebra here. Take my word for it. Solving this equation for K, you end up with this right here. Let's now plug into this equation. Remember, we got delta E at negative 7.2, so let's plug that right into here in the equation. You would end up with this right here. And notice, if you're going to plug in kilojoules for your delta E, the R value is a constant, which happens to be 0.00831, and the question is asking us about room temperature, and room temperature in Kelvin is 298. Solving for K, you would end up with K equals 18, which brings us to the next calculation. Remember, this equation says that KEQ is technically products over reactants. Well, we happened to solve for K in the previous calculation, so that means 18 is equal to the amount of products over the amount of reactants at equilibrium. And for our situation, the amount of product is the amount of conformations that have the methyl equatorial divided by our reactant, which is the amount of conformations that have the methyl axial. And to simplify this, let's write 18 as simply 18 over 1. So what we've just determined here is that let's say you had 19 molecules of methyl cyclohexane. The last expression here is telling us that 18 would be in the conformation with the methyl equatorial, and one of them would be in the conformation of the methyl axial. This helps us answer our question, as long as we use one more equation here, this one. This one says the percent of molecules that are a certain conformation, in this case E, is equal to the amount of E's over the amount of E's plus A times 100. So let's plug into this now. Remember, we said the amount of E is 18, the amount of A is 1, so we get 18 over 18 plus 1 times 100. Solving this for percent E, we end up with this. The percent of molecules with the methyl equatorial would be 95%, and the percent that have the methyl axial would be 5%. This is the answer to the question. Notice this follows what we've previously learned. Think about our two ring structures. Which one is the more stable conformation? Well, that of course is the one on the right, the one with the methyl equatorial. So it makes sense that that conformation should be in a higher amount than the conformation with the methyl axial. So notice we're able to use thermodynamics to do mathematical calculations.